Social dance is practiced in many forms, and it can be difficult for beginners to identify moves they see in the wild. However, that identification would be necessary to search for learning resources. Hence, this project strives to address that by classifying crossed-up waltz figures. A quick overview of some existing works. Pose estimation has been an ongoing point of interest in the field of computer vision, such as with OpenPose and MediaPipe in 2019 and 2020. Still, there are inherent challenges, most notably depth ambiguity and occlusion. In 2026, WAM unified the strengths of OpenPose and MediaPipe with multi-person tracking in a 3D world, and it mitigates the issue of foot sliding or drift, issue from depth ambiguity, by predicting foot-to-floor contact and freezing the foot if necessary. Past works also show different data processing and representations conducive to orientation invariance, as well as the success of transformers on related tasks. Although dance classification has been studied, it has not been done so with multiple interacting people, and the reverse is the same. Methods. A custom dataset was used to be elaborated on in the next section. Feature extraction was performed via WAM, then a basic algorithm was used for identifying the lead follow because WAM may scramble the order. Finally, 3 models, a random forest, a dual-stream transformer, and an MLP were used to classify the data separately. Data. The custom dataset consisted of 10 popular crossed-up waltz figures, recorded at 8 different angles and with role reversal, i.e. with the lead and follow switching, so as not to train on the body dimensions, physical characteristics of the dancers. These 9 to 12-second videos were quantized into 3-second clips, manually checked to extract the ones with the correct phase, and further reduced to obtain a balanced dataset. The hyperparameters for the experiments are listed in the paragraph shown. Results. The random forest model had, surprisingly, the highest test accuracy, and the confusion matrices for the 3 models are shown here. Key observations being that the transformer model had perfect precision with pivots, look at the columns, and whereas pivots were among the lowest precision for the other 2, and the MLP mispredicted all orbits as basics. Quantitative analysis reveals that the main difference between the basics and pivots is the rate of the turns. Pivots are twice as fast. This explains why transformers, which performed worse overall but are structured to learn relationships between frames, such as velocity, were able to outperform the other 2 models, which interpreted frames as flattened independent features. Not pictured, but orbits and basics differ only by the open-closed arm positioning and torso direction. Because the differentiation is concentrated into such a small subset of features, random forest, which makes decision boundaries on a random subset of features, had an advantage in classifying orbits. So, transformers were not the most successful model, perhaps because of my frame-precise data alignment, which kind of takes away the time, position, and variance advantage of transformers, makes all of the flattened features more meaningful for basically giving random forest and MLPs a boost. Data collection was fun but grueling, and there's a lot more interesting work to be done in exploring the impact of feature engineering.